Okay, so let's start off then. For those of you who've been taught by me before, I like teaching on the blackboard, and this is one of these things where, unfortunately, with where we find ourselves in the world right now, access to blackboards and in-person teaching is a little bit limited. So I'm doing my best, and this is my simulation of a blackboard. So just by way of tentative outline, and I say tentative here because this may change depending on on where we go and what we find interesting as we go along. But an outline of what I'd like to cover in this course, and again, this is what you would call the mathematical framework underpinning quantum mechanics, quantum field theory, and by extension, something like string theory. And we're going to be focusing largely on analysis. On applied analysis, if you want, in this course. By way of possible textbooks that you could refer to, let me give you some indication here. Let's say recommended. Reading. Some of you who I've taught before may already have access to this, but some of my notes, some of what I'm going to be teaching is coming out of my my own book in preparation, and this is called Tools for Mathematical Physics. It's in preparation to be published by Cambridge University Press, but it's one of these I'm getting there logarithmically kind of stories, so it's not yet available, but I will put it up on Vula, and I will email a copy to everybody on my SATS mailing list. So you will have a copy of this. It's quite detailed, and it's really a textbook that covers from first year through to master's level in mathematical physics, and it largely covers the material which I am going to take roughly for granted. It's material that everybody ought to have covered at some stage in their undergraduate curriculum. But if you haven't, it's covered in fair amount of detail in my book. My notes, if you want. So those are the lecture notes for this course. The lectures themselves are very detailed, as you're going to see as we go along. And I like to think that my handwriting's decent, and you can take down the notes as we're going along. And again, because they're recorded, you have access to these as long as you have access to either Vula or YouTube. The standard book in this field is Mathematical Methods. For Physicists by Afkin and Weber. And you can find this in any online bookshop. And it's really the standard in the field. Everybody has a copy of it. It's a good book. It's really nice, but it's not particularly deep. It does have a lot of examples and a lot of applications, which are great, but it doesn't go into topics in a great deal of depth. The book that does, and everybody just knows it by the authors, is Moss and Feshbach. And much of what I'm going to be telling you about is an adaptation from Moss and Feshbach. So Mawson-Feshbach is not easy reading. It's certainly not, first reading in mathematical physics. But, if you read the book enough and you stick around in the field enough, you start to learn that most mathematical physics textbooks are really adaptations of Mawson-Feshbach. It really is this 2-volume set that constitutes, it's like the Bible in the field. So there's 2 volumes, 1 and 2. They cover a slightly different material. I draw on some of this, but I also expand on it, and I've adapted it for the material that I want to cover. So speaking of the material I want to cover, we're going to start off by going over some material that you may not be familiar with from complex analysis. Certainly the UCT students, I think I know what you've covered in your complex analysis course. And this will be in addition, it'll be topics in addition to that. For those of you who may not have familiarity with, a lot of familiarity with complex analysis, I don't really care too much about the analysis part of complex analysis. What I care about is the ability to do integrals. And so I would recommend Afkin and Weber for that. They have a great treatment of all the materials that we need for this course. And once we get a handle on that, we're going to use some of these techniques to revisit basic first and second order differential equations, ordinary differential equations, but differential equations on the complex plane instead of the real differential equations that you may have seen in your first and maybe even second courses in differential equations. So these will be complex differential equations, and we're going to see that when you apply the theory of complex functions to these complex differential equations, there's an enormous amount of power that you get in being able to solve these differential equations, or rather in being able to write down solutions for these differential equations without actually solving the differential equations. In much the same way that if you think back to when you first learned about, let's say, the logistic differential equation, you tended to not go straight ahead and solve the logistic equation. You wrote down a solution based on the structure of the differential equation, and you're able to read off, for example, what the late time asymptotics of those solutions were, basically just by looking at the differential equation itself and not actually, doing the integration by partial fraction decomposition or whatever technique you want to use. So we're going to be playing the same game with much more complex differential equations, literally as well. Okay, then we're going to move on and develop the theory of special functions. You will have seen some of these special functions before. For example, the gamma function. We're going to take that and we're going to develop them a little bit more. So from the gamma function, we're going to go to the beta function, which plays a central role in the history of string theory. The beta function, of course, being what we call in string theory the Veneziano amplitude for string scattering. So we're going to be developing the theory of these functions, and we're going to give integral representations for these functions. Again, the name of the game is I want to be able to write down a solution. I want to be able to write down a function. And I want to be able to expand on its properties without actually necessarily carrying out the integral. Okay. Again, you've seen some of these before for those of you who've done even a first course in Fourier analysis. Much of Fourier integrals, much of Fourier integral theory is really the theory of Fourier representations. So there you tried to carry out the integral as much as you could, but sometimes you couldn't. And what we're going to see is that sometimes you don't need to. You can just write down the integral representation, don't do the integral, but still read off the properties of the function. And this will take us to the theory of what's called resolvents. And I'm going to mix resolvents with kind of advanced topics in Green's functions. Again, we're still solving differential equations, and we're going to be applying these things to, for example, the quantum mechanics of the quantum harmonic oscillator or the hydrogen atom, kind of prototype quantum mechanics problems that we're going to apply spectral analysis, specifically the theory of resolvent operators and Green's functions as inverse operators to standard second order differential operators, to try and explore. And then if we have time, I will, and we almost certainly will, I will tell you, I will introduce another topic which is typically not spoken too much about in undergraduate courses, and this is the theory of integral equations. And so if you think about differential equations, a differential equation is an equation that has a function that you're trying to solve for and its derivatives in the same equation. And so to solve for that function, you have to integrate the equation. Integral equations are similar but different in the sense that they involve a function that we're trying to solve for, but they also involve that function under an integral sign. And so in order to solve for the function, you would assume that you have to differentiate the equation, but then if I differentiate the equation, I'm back to the point where I have now a function and its derivatives, which would require me to integrate the equation. So we're going to see how to resolve this dilemma, and this will introduce us to the theory of integral equations and its applications in mathematical physics. So let me stop before going on and ask if there are any questions at this point. And if I'm going too fast or too slow and you would like me to pick up the pace or slow down the pace, please just raise a hand and ask a question. I like to keep my class interactive. This is why I'm not just recording lectures and putting them up. I want to interact with you guys. And I get the feeling that, or at least I got the feeling last year that, after nearly 2 years worth of pandemic learning, many people want that kind of interaction as well. Okay, so again, feel free to stop and ask me questions. I'm not particularly concerned about covering a certain amount of material for this course. I am concerned about you guys actually learning the material that I'm trying to cover. Okay, so let's get started then. And by way of introduction to my teaching style, I always start off each class with an outline of what I expect you to learn out of this, and we'll come back and tick them off as we go along. Okay, so today I want to cover, today is basically a warm-up lecture, and we're going to talk about some very general things, which if you've done at least a course in differential equations or dynamical systems, this stuff would be familiar to you, but maybe not in the language that I want to talk about it now. Good. So let's. So today we're going to talk about. We're going to define an index of a curve, and this is really a story about vector fields in 2 dimensions, and we're going to apply it to computing the indices, the index of a curve around certain fixed points of differential equations. I'll define all of these things as we go along, and I'll end up by showing you how this is related to a topic that you may or may not be familiar with, and this is the idea of winding numbers of curves around points in the complex plane. Okay, so let's start off by thinking about a vector field generated by a differential equation. So suppose I have some differential equation, and I'll put it in vector form. So x here, specifically this x, is a vector in the plane. So it consists of x and y. And my differential equation is x dot equals some function, some vector valued function of the vector x. And the differential equation defines for me a smooth 2-dimensional vector field, by which I mean that this function f is a smooth, meaning infinitely differentiable function. It's an element of C infinity. And it's a two-dimensional vector field, so it's a two-component vector. And I'm going to consider some simple closed curve on the plane. By a closed curve, I'm going to distinguish a curve like, sorry, let's go back here. So a curve like this, for example, is an open curve in the plane. And a curve where I identify the ends is a closed curve, okay? And a simple curve is a curve like this closed curve, whereas a non-simple curve is one that, for example, crosses itself, like such. So if I allow crossings, then I have a non-simple curve, and if I don't allow crossings, then I have a simple curve. So suppose I have a simple closed curve now, okay? In the plane. So something like this. And the red arrows in this picture correspond to, the red arrows in the picture correspond to a visualization of my vector field. Here I've written it as R, but really it should be the vector X, and the vector X here consists of components X and Y. And for each point in the plane, I can draw an arrow. And that arrow is a vector, and the set of all those vectors defines the vector field for me. And the blue curve C is the curve that I'm interested in. Okay. Now, I can write down some coordinate system on the plane, like here. This means drawing coordinates on the plane. Sorry, let's pick a color that's noticeable. Right, so we can draw a set of coordinates on the plane, and then I can resolve each of these vectors into its components, into an X component and a Y component. And then if I take the inverse tangent of Y over X, so this guy, that defines an angle that that vector makes with the X direction, if you want. Okay, and I can do this for all of the vectors in the vector field. Just visit them point by point and compute the angle associated to them. Is that clear?
Yeah, that's clear.
Good. Okay, so now we have a smooth two-dimensional vector field and some simple closed curve in the plane. What do we do with it? Well, suppose I pick a point on my curve and I make a complete circuit of the curve. So I go around the whole curve, the whole blue curve C. So let's go back to that picture. So I go back to the whole blue curve C, and I pick some point. Let's say here, doesn't matter. And I traverse the curve. And by convention, we'll traverse the curve in a clockwise fashion. Oh, sorry, in a counterclockwise fashion. And we'll count going counterclockwise around the curve positive, and going clockwise around the curve opposite orientation, we'll count it negatively. In the same way that you would do for traversing curves on the complex plane in complex analysis. Okay. Very good.
So are we doing a line integral around, or what are we doing?
We're not talking about doing integrals at this point. We're just talking about walking along this curve on the plane. That's it.
Okay.
Okay. We'll talk about integrals a little bit later, and it will be line integrals in the two-dimensional vector language, but just integrals on the complex plane in the complex language. And we're going to be focusing on the complex language here. Okay.
Okay.
Good. Okay, so take a look at these vectors, right? So suppose I start off now here with this guy, right? And I'm walking around the blue curve in the counterclockwise direction, and I'm keeping note of each of these arrows, right? As we go along the blue curve, until I get back to the original point I started off with. So I make a complete circuit of the curve. So what happens? Well, a complete circuit of the curve C will result in a phase change of the vector. So as I go along, my vector is changing, and it comes back to the original vector. But it comes back to the original vector, possibly with a phase change. But that phase change can only be an integer multiple of 2 pi. Okay? So draw the picture, draw some arrows, follow the curves, and you'll see that that's a clear statement to make. So a complete circuit of the closed curve will result in a phase change that is an integer multiple of 2 pi. Now we can use this fact to define what we're going to call the index of the curve C with respect to the vector field f of x. And we define it as follows. We make a complete circuit of the curve C, and we count the total change delta phi of the vector field as we make that complete circuit, and then I divide by 2 pi. Dividing out by 2 pi will single out just this integer multiple that we're looking for. And that integer multiple, that integer specifically, is what we will call the index of the curve C with respect to the vector field. Okay. So let's do some examples to make this clear. So again, delta phi is the net change in phi, in the angle, over a complete circuit of a complete traversal of the curve C. And the index counts the number of counterclockwise rotations of the vector field as we traverse the curve. Okay, so let's consider some examples. So the example on the left first. Here's a vector field, and I've taken the liberty of labeling the points on the vector field. So here's 1, 2, 3, 4, 5, 6, 7, 8, 9 as I go along. Right? So the vector field is given to me. The curve C, which is the yellow ellipse there, is given to me. And I'll start at 1, and I just want to keep track of the phase of the vector field. So following phi as we go along, right? Starts off here, makes a full rotation. When I come back, it's rotated by 2 pi. So 2 pi divided by 2 pi, and the integer multiple we're looking for, the index of the curve with respect to this particular vector field, is just 2 pi over 2 pi, and that's just 1. Is that clear? Anybody can just pipe up and say yes. If it's not clear, then let me know, and I'll say it again.
Can you please just say it one more time?
Okay. So take the position 1, take the vector located at position 1, and follow me as we go along the curve. Remember, we're going in the counterclockwise direction. So just follow the arrows, right? It starts off here, it goes around 7, 8, 9, back to 1. Okay. Can you see that this vector has made a full 360-degree rotation, or a 2 pi rotation? In which case, the delta phi that we're counting is 2 pi. Change in phi is 2 pi. And 2 pi divided by 2 pi is 1. So we say that the index of this curve with respect to this vector field is just 1.
Okay, thanks.
Okay, so to contrast this, take a look at the example on the right. So now let's say we start here and we go 2, 3, 4, 5, 6, 7, 8, 9, back to 1. Now there's the vector field. And I'm going counterclockwise, and this guy is rotating like that. So now can you see that as I go along the curve, and I get back to the original vector that I started off with, delta phi is in fact minus 2 pi. So the index there is minus 2 pi divided by 2 pi, and that's minus 1. Make sense?
Yeah.
Okay.
Could you go over that bit again, please?
Right. Again, watch the vector field, right? I'm starting off here. So watch the vector field. As I'm going along in the counterclockwise direction, it goes like this. In skateboarding, you call this an alley-oop. You're turning in the opposite direction to which you're moving, right? So it goes like this. In this case, I is minus 2 pi because the vector field is rotating clockwise. We're traversing counterclockwise. So I is minus 2 pi over 2 pi, and that's minus 1. Okay. All right. So now I'd like you to go back and think about the first time you saw this material on differential equations, maybe dynamical systems. You were studying vector fields, you were studying flows of vector fields, right? So I had some vector field generated by a differential equation x dot equals f of x. And there are some special points in the vector field at which nothing happens, right? So if I'm at that point, then nothing happens. And nothing happens means that there's no change from that point, okay? And no change from that point means that x dot must equal to 0. But x dot is equal to f of x, so if x dot is equal to 0, then f of x equals 0. So then I solve the algebraic equation f of x equals 0 for x. All points x that satisfy f of x equals 0 are what we call fixed points of the dynamical system. In other words, if my dynamical system defines a flow for me, then at the fixed point, if I'm sitting specifically at the fixed point, I don't go anywhere. It's fixed in time. Okay? So that's what a fixed point of the vector field is. So I solve the equation f of x equals 0, this equation, and that will give me the fixed points. Okay. Now we can use this notion of a fixed point to write down some properties of this index that we just defined. In particular, imagine I have my curve C and I deform the curve. Okay, imagine my curve C is some piece of string that lies on the plane, on a tabletop, for example. And I can move this piece of string by deforming it. And every movement I make deforms the curve into another curve. Let's call it C tilde. The deal is, if I can deform my original curve C into a new curve C tilde, and I don't pass through any of the fixed points, these guys, if I don't pass through any of the fixed points of the vector field, then the index of my first curve with respect to that vector field is the same as the index of the second curve with respect to the vector field. The reason why this is a useful thing to know is because sometimes computing the index for one curve is much easier than computing the index for a second curve. And if they happen to be the same index, if the index is invariant under that deformation, then great, I can just deform it to the simplest possible curve, compute the index, and be guaranteed that it'll be the same as the index that I'm looking for. Okay. The next point to note is that if the curve C does not enclose any fixed points, then its index is 0. And the reason for this is because of the first point. I can always deform this thing. If it doesn't include any fixed points, I can always deform it to a point, in which case the index through that is 0. Nothing changes as I traverse the point because the point is a point. Then finally, if I reverse the direction of the vector field, so I take each of the arrows. So let's go back to the picture that we were working with here. All right, take either of these two pictures and imagine changing the direction of every single arrow. Just flip the direction of every single arrow. Go around the entire vector field and flip all the directions, and then do the counting again. You will find that nothing changes. In other words, the index is invariant under a change of direction of the vector field. And by change the direction of the vector field, I mean just replacing f of x with minus f of x. So there's three things that we've just learned. If the curve C is deformed into another curve without passing through any fixed points, then the index is invariant. If the curve C does not enclose any fixed points of the vector field, then the index is 0. And if I change the direction of the vector field by just adding a minus sign in front of the f of x, the index is unchanged. It's invariant. The next point to note is that if the curve C is what we call an integral curve of the differential equation. So geometrically, what that means is that if I draw the curve C and I draw the vector field on the same picture, then the vector field will be tangent to the curve C at all points. If that is the case, then we say that the integral curve, that C is an integral curve of the differential equation. And the story here is that if I have an integral curve of the differential equation, then its index is always +1. And you can convince yourself of this fact by drawing a picture. Draw a curve, make the vector field that you're working with the tangent vector field to every point on that curve. Start at one point, come back to that point, and compute delta phi, and you'll see that it's 2 pi. So 2 pi over 2 pi is 1, and the index is necessarily 1. Okay. Finally, I'd like to note that if suppose x star is some isolated fixed point. So it's a fixed point, and I can always draw a neighborhood of this fixed point sufficiently small, and I won't find another fixed point of the differential equation within that neighborhood. Then I'll say that x star is a fixed point, and it's an isolated fixed point. Then the index of x star is defined to be, this should really be defined to be here. It's defined to be the index for any closed curve that encloses only x star. In other words, I have some fixed point. It's an isolated fixed point, so I don't find in its neighborhood another fixed point. If I want to know what the index of that point is, all I have to do is draw some curve, some closed curve that encloses it, make sure that it doesn't enclose any other fixed points, and write down the index of that curve, and they will be the same by definition. So in the theory of differential equations that you may have encountered before, there are some special types of fixed points, right? One type of fixed point is what we call a stable node. So if I draw a vector field around the stable node, all vectors point toward the stable node. And you can imagine that, you know, the vector field is some flow of a fluid on a plane. A stable node is one where if I put a leaf on that fluid, say, if it's water flowing, then it flows toward the fixed point anywhere that I choose to place the leaf, right? So the stable node is a sink in the fluid flow, right? On the other hand, I have an unstable node, and an unstable node is a source in the fluid flow. So here, if I put a leaf anywhere around the unstable fixed point, it always flows away from that point in any direction. So that's the green vector field that you're seeing there. And then you have vector fields that are what we call saddle nodes. And saddle nodes have stable directions, the vertical directions in this picture, and unstable directions, which are the horizontal directions in this picture. And you can see that if you follow the vector field, they will follow those two submanifolds, the stable submanifold and the unstable submanifold. Now, using this picture and drawing some curves that enclose these fixed points, the stable node, the unstable node, and the saddle point, and doing what we've just been doing with the previous examples, follow the vectors, you will see that the index of a stable node is +1. The index of an unstable node is also +1. That kind of makes sense given the property we listed that if you just flip all the arrow directions, the index stays the same. So if the index for the blue arrows is +1, then the index for the green arrows must be +1. And then doing exactly the same thing with the red vector field, you'll count that delta phi is minus 2 pi with a complete traversal, and the index of a saddle node is minus 1. Is everybody happy with this?
Yes.
Right. So this is all drawing pictures on the plane and following arrows on the plane. So let's move toward something a little bit more calculus-y. Right? So suppose I have a vector field, and this vector field has n fixed points in some region of the plane. So let's call the fixed points x1 star through to xn star, and we're going to surround these fixed points with some curve c. So that's this curve here on the outside, right? So that's my curve C. So now imagine that I take this curve C and I deform it by squeezing it into circles around each of these fixed points, right? So just take the blue lines indicating the squeezing directions, squeeze these things around circles around each of the fixed points. And I'll deform the curve C into another curve, let's call it capital gamma. And if I call each of the circles little gamma, so little gammas are circle 1, circle 2, circle 3, all the way through to circle n. Now you realize, of course, that these are not strictly circles because I have to link them with these parallel lines. Okay, and the same kind of story that you've seen in the calculus of complex variables. And the arrows here indicate that I'm traversing the curve C in the counterclockwise direction. And however I deform this story, I have to deform the yellow curve and maintain the orientation. Yes, Anik.
Maybe I missed. How can we write both stable and unstable indices both +1? Can you please repeat once again?
So I would recommend just drawing a curve and doing the counting, right? And you will see that the counting will come out to be +1 in any event. But there's a shortcut to this, which is the fact that we noted that if I reverse the direction of a vector field, then the index of the curve is unchanged. The index of the curve is invariant if I flip all the vectors in my vector field. So if you think about what's going on between the blue vector field and the green vector field, I've done exactly that. I've taken each of the vectors and I've just flipped them, right? That's a minus sign. That's an overall minus sign in front of f of x.
Okay.
So if the index of the stable node was +1, then the index of the unstable node must be +1 as well.
Okay, thanks.
All right, good. So back to this picture. So now my curve gamma, capital gamma, is the union of all of the circles as well as the parallel lines. But you can see that every time I traverse a parallel line, in this direction, I'll go back in that direction. And so whatever contribution I'm getting from the parallel lines is going to cancel out. So really all that's going to matter in this index counting are the circles gamma I. Okay. However, in going from the curve C to the curve gamma, I don't pass, by construction, I don't pass any of the fixed points. In other words, the index of C and the index of gamma must be exactly the same. But the index of gamma is the sum of the indices of all of the circles little gamma. Right, so now I should tell you about another property of my course, which is that you will find that as we go along, the course will be littered with text in orange. This is not for handing in, this is for your own education, but I strongly recommend that you do it. These are all exercises. So again, these are not exercises that I expect you to hand in, but they're exercises that I expect you to do in order to keep up with what we're doing. The first exercise is using the information we've just talked about. I'd like you to show that any closed orbit in phase space, so this is phase space, meaning the spaces of x and x dots. Any closed orbit in phase space, and if you're not familiar with the terminology, Google it, must enclose fixed points whose indices sum to +1. Okay? I want you to show that. Anik, is that a new hand or is that the old hand?
It's the old hand, but I
Okay.
don't know how to erase. Yeah, okay.
I can put it down for you, but good.
So I'm
So-
not very much familiar with this Zoom system, so I'm sorry.
By the end of this course, you will be. Okay, so I want you to show that any closed orbit in phase space must enclose fixed points, some set of fixed points. And the key thing about those fixed points is that if I add up the indices of all of those fixed points, they must add up to +1. A corollary of that statement is that any closed orbit in the phase space must enclose at least one fixed point. Okay, at least one fixed point. But given what we just said about the indices of stable nodes, unstable nodes, and saddle nodes, if there is only one fixed point that it encloses, that cannot be a saddle. So if a closed orbit in phase space encloses only one fixed point, then it can only be a stable node or an unstable node. It cannot be a saddle node because then the index of that is -1. Okay. So finally, let me point out before we close for the day that this idea of the index, for those of you who've done this in complex analysis, the idea of an index is suspiciously similar to what one would call the winding number in the theory of complex functions. So what do I mean by that? Well, suppose I have some point zi in the complex plane, and I enclose that point by some simple closed contour, C. So now, Justin, I am talking about doing integrals, and I'm talking about doing integrals in the complex plane. And if you remember from your complex variables, any integral in the complex plane, any single integral in the complex plane, I can frame as a two-dimensional integral on the real two-plane. Okay? So consider doing the following integral. Suppose I do the integral dz over z minus zi, zi being this point in the complex plane. Okay? And I want to do a closed contour integral of 1 over z minus zi with respect to z, and then I'll divide by 2 pi I, because when you do complex analysis, you always divide by 2 pi I. So I can think of this as a complex line integral, and the integral of 1 over z minus zi is just log of z minus zi. And then you have to evaluate that over the closed contour C. Now, you can legitimately object to this, that the logarithm function is multi-valued and blah, 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 and I honestly don't care. Because when I evaluate this over the complex plane, all that matters is this guy, the delta theta I. Delta theta I here is nothing but the total change in the argument, modulus argument form, the total change in the argument of z minus zi as the function z traverses the curve C around the point zi. So there's a fair amount of information here. Just stop and think about it for a little bit. Delta theta I counts the total change in the argument of z minus zi as we traverse C around the point zi. As such, this function w of zi is counting, when I divide it by 2 pi, having done this integral, it is counting the number of times the curve C winds around the point zi. So w of zi here goes by the name of, in the literature, it goes by the name of the winding number of the curve C around the point Zi. Any questions? Okay, so what we're going to do next time, which is Thursday, is we're going to develop this idea of the winding number of a curve around a particular point in the complex plane and use it to generalize Cauchy's theorem. So Cauchy's theorem, you remember, tells you how to compute integrals in the complex plane by evaluating the residue of the integral, the residue of poles at particular points on the complex plane. But I will guess, I will make an educated guess that all the integrals that you've seen up to this point where you've used Cauchy's theorem to evaluate integrals have been taken with simple closed contours like the curve C that you're seeing here. In particular, you probably never did an integral over something like a figure 8, which is a non-simple closed curve. So that's what we want to do. We want to use this idea of the winding number of the curve to generalize Cauchy's integral theorem to tell you how to calculate integrals over things like figure 8 curves. Okay? Any questions?
Yes, I have a question.
Sure.
Yeah, so we started from the real two-dimensional vector space where we define indices. And
Yep.
then we make analogy with indices to the winding number in complex plane. Is it?
Yes?
Okay. Okay.
Sorry, was there a question?
No, it's just a clarification. That is,
Okay.
we started from here.
Yeah, that's what we did. Cabello?